Hello everyone and welcome to part 6, yes, part 6 of And To Be Astronomer reacts to the Flat Earthers' alternative to gravity, also known as Incoherent Electrostatic Acceleration. We are at part 2, which curiously has kind of been, been a year between those two parts, if I recall correctly. Yeah. Curious. No, nevertheless, let us have a look. Maybe they have refined some of the ideas that they had 1 year and a bit prior to that.
Hello, everybody out there in YouTube land. This is Good Times for All, or Zachary Zabala if you prefer. In this video, we'll be taking a deeper look into Incoherent Electrostatic Acceleration, and we'll be calling this Part 2.
Alright.
I was happy to see so many grasp the concepts of the laws of electricity, but
I mean, if those had anything to do with the things that you talk about, that would certainly have been nice.
Still see some having issues connecting all the pieces together. I am fully to blame, as I realized I did not touch on the subject of acceleration at all, and for this I apologize.
Hey, credit where credit's due.
It was an oversight we will try to remedy in this video. If you haven't seen the first video, I recommend watching it first, before
I can't
continuing along here. The link is in the description below. First off, if you didn't notice from the first video, gravity...
So, turns out, if I enter full screen mode, my recording stops. So I will not put it into full screen, I'm sorry for that.
And is only trying to explain the path of the luminaries above, i.e., and is only video. First off, if you didn't notice from the first video, gravity does not affect anything down here on Earth.
It does.
And is only...
Why would you say that? It clearly does, right? And the citation that he has here, that the theory of gravitation, the description of blah 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 blah, long-range forces that electric and neutral bodies exert on one another because of their matter content. I don't necessarily disagree with that definition. However, it's not solely for long-range forces. Certainly, you would derive it over long-range forces, over long-range scales, right? Because the effects there are more pronounced. You can see from this very thing, because they have CGS units right here. That's now we have SI units that are based on kilogram, meter and second, and the old ones were based on centimeter, gram and second, right? So you can see from that one that this is a rather old thing that he shows here. I don't know what this is. It has an EDU at the end, so it's probably fine. Well, it's pretty certainly going to be fine. But it's not solely there to explain the movement of the luminaries. It was first, the first person who really put much thought into it was Galileo, actually, with his sloped acceleration experiments that I believe I talked a bit about in the part 1 of this video series. So that's just a straight up lie.
Only trying to explain the path of the luminaries above, i.e., the sun, moon, stars, and solar systems in the heliocentric model of our...
Again, that's just wrong. I don't know what else to say here. That's just not true. When I drop a pen, that's due to gravity. Full stop.
our universe. I will once again show...
But why is he underlining electrically neutral bodies here? That's because you look at all of these forces separately, right? When we talk about electrodynamics at university, we just... because then this would complicate things greatly, right? When we talk about gravitational physics, we look at only electrically neutral bodies. So to get the basics right, and once you have all of the forces for one of these cases, or for both of these cases separately, you can just combine them. Forces add up, right? So that's why he underlined electrically neutral bodies there.
Show former physics professor of MIT for 4 decades, Dr. Walter Lewin, explained this in simple terms.
So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces.
I agree.
On an
Completely.
atomic scale, up to thousands of kilometers, it's really electric forces.
I believe by what he says by holding it together, I believe he refers to the forces that keep a body as a solid, right? I've said in the first part, I also believe in for this series, I mentioned that I don't completely agree. I would say hundreds. I believe thousands of kilometers is a bit of an overstatement, but all of the solids are on scales that are above the atomic scale, hold together by electromagnetic force, by the electromagnetic force, right? I believe that that's very much what he means, is being held together, and I can't disagree. My table is being held together by the electromagnetic forces. That's just a fact. My gravity does not need to exist for my table to be as stable as it is, and that rhymed, so you know it's true. So I very much believe that that's what he meant there.
That hold our world together. But on a much larger scale,
Yes.
planets and stars and the galaxy,
We have said that in the first video, the lights in the sky. Well, yeah, those are the lights in the sky. But, I mean, they are a bit more than that. They can be seen as lights in the sky, but, you know, only by people who kind of don't know what they really are.
it is gravity that holds our world together.
Yes.
Now you may say, that's very inconsistent with what you just told us, because didn't you tell us that D cancels if you compare gravity with electricity?
Yes, but keep in mind that most objects in the universe have only a very small amount of charge per unit mass.
Well, I've attested to all of this in the first part. I'm not
Earth,
going to go over it again.
large buildings are dominated by electric forces, rotated by gravity.
Electricity that holds our world together.
On an
Yeah.
atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together.
See?
Yeah.
Then he stated that not until
That's fine.
referring to moons, planets, and stars does gravity take effect.
Well, again, he doesn't say that they're only then taking into effect. He says that they become by far the dominant part. You can have small influences that are still there, and I completely agree that those are very small influences. I can hold a magnet easily in my hand that lifts up a paperclip from my desk. That is very, very easy. That is because compared to the electromagnetic force, gravity is rather weak. But on very, very big scales, I couldn't do that even closely as easily as I can. But that doesn't mean that those smaller forces or those weaker forces don't have an influence.
On a much larger scale, planets and stars
Also, by that, I'm implying that Walter Lewin believed the Earth to be flat and controlled by incoherent electrostatic acceleration.
and the galaxy, it is gravity that holds our world together.
Any physicist worth their weight in salt knows
My weight in salt, well, that's not particularly worth then, right? But, okay.
that the electric forces here on Earth are 1,000,000,000.
You know that we have scientific notation for a reason, right? So that we don't have to do that.
0,000,000,000. You know what? I lost count. Too many zeros. So we just say 10 to the 26th power. Anyone arguing about Newtonian or Einsteinian types of gravity are only speaking about the lights in the sky,
No.
or are over 150 years out of date, as this was well understood when Maxwell wrote his equations. This was the reason the ionosphere was created over 100 years ago,
The ionosphere wasn't created, it was discovered.
with no test to show it even.
I'm only a physicist with nothing material to show for my neighbors. I've never seen the ionosphere, although I have felt the subject for years. Well, I mean, seeing the ionosphere, how are you exactly planning on seeing it, right? It's you can't typically see charges, so, you know.
Possible to occur, how they claim. It is clear that
It's
many of
not,
us who were not
well,
educated much further than high
he's
school
just
in
saying
physics
that.
were never taught this at all, and makes me wonder why they would tell anyone gravity holds them to the Earth. That was one part of the first video that some had overlooked and I thought was crucial to see. This is taught
Alright.
in the mainstream, high education curriculum, and is not something new we are sharing. Now that we have that out of the way, I would like to apologize once more for leaving out the acceleration part of the topic, as it is one of the most important parts to help us comprehend that there is a vector, or downward bias here on Earth. Remember, a vector is an indicator showing what direction matter will go, depending on the...
A vector. The strictly mathematical definition of a vector is an element of a vector space, which is not helpful because it's a definition that comes from mathematicians. The definition of vector I would give is some quantity that cannot merely be described by just one value. It needs to have multiple. For example, my personal favorite always is velocity, right? Because velocity is not just I'm moving at 10 meters a second. The velocity really means I'm moving in that direction, right? In our day-to-day lives, we use three-dimensional space to express that. So you have a free vector, which is what it's called sometimes, where you have an x component, a y component, and a z component, and some value in each direction. And from that, you can clearly determine how fast you're going and in which direction you're going. That's how I would explain a vector. So a vector is more than what he said. And I mean, he obviously applied it to his example, but yeah.
surrounding electrostatic field compared to its own electrostatic charge, and at what potential it will travel.
He uses potential for everything. He has no clue what the words mean. It doesn't travel at a potential. It can travel at a certain velocity. It can travel at a certain speed. Note that speed and velocity are two different things. Speed is just the value of velocity. So for me to say I move 10 meters a second would be a speed, and a velocity would contain information about the direction, right? Things aren't moving at potentials. A potential, as I mentioned earlier, is the amount of work you would need to put into a system for it to gain the amount of energy that the potential says, right? So a potential of 1 joule, for example, would mean that you would need to put in the amount of work or energy of 1 joule to get it there. Or this may also be set free by a movement, depending on how I define your negative and positive values.
Here on Earth, we have an electrostatic gradient in the atmosphere that rises in potential the further you get from the surface.
That statement, however, is... So this again is fine. I believe I know where he has that from. It's from the Feynman lectures. Yeah, clearly from the Feynman lectures. No sources to be seen anywhere, which is always nice. The Feynman lectures, I can only greatly recommend those. It also explains it later. I wanted to mention that you can see here that the daily variation in the atmospheric potential gradient. So it changes daily, since he clearly thinks that the Feynman lectures are a valid source. I would like to show you this picture. Shouldn't we then change in acceleration every day, measurably so by about 10%? He doesn't talk about that, of course, because it would destroy. Either he doesn't know, then he hasn't done particularly well research, or he knows about it and is withholding it, then he's lying, you know?
The potential grows 100 volts every meter linearly as you rise
Roughly, on average.
from the plane, which indicates we are between two Gaussian surfaces.
It does not.
This you may remember from the first video, but what I left out was that only in one direction do things accelerate. Comprehending this is key
Why
to seeing
so
the
then?
bias in direction. The only direction that matter accelerates naturally, and with no outside force made by an animal, plant, or mineral, is toward the Gaussian surface with less potential.
Didn't he just say there were two Gaussian surfaces? And also, a Gaussian surface doesn't have a potential. There's a potential between the two. because voltage is defined as a potential difference. So if you have voltage between two of these things, that essentially means that you have potential between those two surfaces. Neither of these surfaces on its own has a single potential. That again shows me that he doesn't know anything about electrodynamics. Well, not even electrodynamics. He struggles with electrostatics too, clearly.
better known as Earth. This acceleration is very weak at small distances, yet can be very destructive at large ones.
Yeah, I don't know what he's measuring there. There you have a force in Newton, and you have an acceleration in meters per second squared. Oh, okay. More information about this plot, please. What are we supposed to see here?
The distance we are concentrating on
Cool.
is a vertical one, along the vector created by the Earth's electric field.
Again, I'm sorry. I'm a bit tired today. I need to hear the sentence again.
Yet can be very destructive at large ones. The distance we are concentrating on is a vertical one, along the vector created
He means the direction is vertical.
by the Earth's electric field.
Again, if you were to, why doesn't it change around electricity towers that conduct hundreds of thousands of volts of potential difference? Why is it not different around there?
Imagine dropping a bowling ball onto a couch from around 6 inches.
Yes.
It would make an indentation into the cushion, coming to rest in the center, and the couch would be in good working order after you lifted it off.
Probably.
Now we will drop
Not all couch was scrap.
the ball from around 10 feet up. And instead of the ball remaining on the cushion, it might now bounce off due to the potential it had when it made contact with the couch.
It had no potential when it grabbed the couch. From kinematics, you would say that when you lift an object up, you give it potential energy, and when you release it, it exchanges this potential energy for kinetic energy. And when it touches the couch, which is basically the floor in our experiment, it will have zero potential energy left relative to the couch, and it will have reached its maximum in kinetic energy.
Causing a much larger reaction of the cushion and spring.
What do you mean reaction of the cushion? It's just that all of this kinetic energy has to go somewhere, because energy cannot be destroyed, right? It needs to go somewhere. Where it is going, in practical terms, is it is going into the deformation energy of the loose grid structure that you have in the material that the cushion is made of. A bit goes into thermal energy, because you always have that in any reaction almost, and a bit goes into the creation of sound, because you can hear it. Those should be the main three.
Springs beneath. It gained this potential because it traveled longer along the vector line that caused it to accelerate.
Well, no. I mean, okay. So what he's doing now is he's trying to say that, well, if you have an energy over applied over a certain length, over a certain line almost, that then you end up with proper energy, right? Which is he is onto something there. I need to remember what the Wikipedia page is called. Essentially, right? Essentially, what's going on here is that if you have an energy field, or like an electric field, and you multiply it, or in physics case, you integrate the electric field times some sort of distance, you then come out, I believe, with a voltage. I will need to double check on that, but yeah. So that's, I believe, where he's going to. He still hasn't explained how this acceleration manifests then, and he still hasn't offered any numerical values, because he has values for the voltage levels in the atmosphere, right? Why can't he simply apply them to show that it would come out with 9.81 meters per second squared? Why doesn't he do that? Because it wouldn't, clearly. Because first of all, he would need to show that the bowling ball is charged in exactly that amount, so it would reach that acceleration. Oh, by the way, we had 18 minutes. Yeah, we have come very far this part. I'm proud of myself. With that, I thank you very much for watching once again, and maybe consider leaving a like, and dare I suggest you even consider subscribing. And I thank you very much for watching, and I'll see you in the next part. Well, I won't see you. You'll hear me, essentially, in the next part. Goodbye.